Hello everybody. In this video I'm going to show you how to find out the moment of inertia for composite body. Okay, but before that let's talk a little bit about moment of inertia. What is actually moment of inertia? It's actually very difficult to define what is moment of inertia. Okay, it's a concept that when we try to find out the stiffness or deformation of a beam or the bending stress, then we see a term that comes when we try to find out those items, which we call that moment of inertia. Okay, so for now you just try to learn how to find out the moment of inertia, and in your future class like mechanics of solids and structural analysis, you will learn why we try to find out the moment of inertia. Okay, so moment of inertia is something like this. Let's say this is my x-axis and y-axis. Here is any body here. Then let's say this distance is y. So this is a small area dA. So your moment of inertia along x-axis is basically y squared dA. Okay, y squared dA. Sometimes we also call that one double moment of area. Okay, because you can see there is a square here. Okay, y dA is actually the moment. When y squared dA, sometimes we call that one double moment of inertia. Okay, double moment of area. Now, similarly, if you see like your y-axis, and if this distance from here to here is x, then basically your IY would be x squared dA. Okay, now we are not going to learn how to find out the moment of inertia for different geometric shape, because that's not that common, like in practical life. Most of the time it's kind of a composite body. Okay, but if you want to find out the moment of inertia for a composite body, then basically you have to know the moment of inertia for very simple shape like rectangle or triangle or circle, half circle, semicircle, something like that. If you know that one, then basically finding out the composite is not that difficult. Now here I'm gonna show you how to find out the moment of inertia for a rectangle. Okay, so let's say this is a rectangle. This is total height is h and total base is b, and this is your centroidal axis, means like the axis that passing through the centroid, right? For rectangle, you already know that the centroidal axis passes through the middle, right? If you see from here to here, that's actually middle, because this is b by 2, and from here to here it's h by 2 here and h by 2 here. Okay, now if I take a very small strip here, then this one, let's say, is dy. So that dA would be here, this multiplied by this, right? So b dy, that's your dA. Now what is the centroid for this small strip from your x-axis? So you can see this distance from here to here is actually y. Okay, y. So y quickly is basically y here. Y quickly means this, like the distance of the centroid of that small strip So since this one is so small that we can assume that one is actually y. So your xc means like the centroidal x-axis, okay, the centroidal x-axis. So that would be integration of y squared dA. So I can write that one y squared into dA is b dy, right? So I can keep that b here, and this one would be y cube by 3, and your y can vary from minus h by 2 to plus h by 2, which is basically bh cubed by 12. Okay, so Ixc is equal to bh cubed by 12. Similarly, if I try to find out Iyc, that would be, sorry, Iyc, that would be h b cubed by 12. Okay, so you can see that's actually at the centroidal axis of the component. Okay, centroidal axis of the component. Try to remember that one because we need that one in future. So other shapes, like this is a triangular shape. For this one, your Ixc is actually bh cubed by 36. Here Ixc is equal to Iyc is equal to pi r to the power 4 by 4. Okay, here Iyc is basically h b cubed by 36. Okay, now you have like other regular shapes like semicircle or quarter circle. In your book at the last page, actually they gave you, this is the last page of your book. You can see all those figures here, and they gave you the moment of inertia for many basic shape here. Okay, so I'm assuming that you are going to take a look here and you can find out the moment of inertia in x-axis or y-axis just looking at this page. Okay, now one of the other most important thing is like that you can actually transfer the moment of inertia from your centroidal axis of that component to any parallel axis. We call that one parallel axis theorem. Okay, parallel axis theorem. I'll show that theorem to you. Let's say I'm trying to find out any parallel axis of xc, which is, let's say, xc prime, okay, which is at a distance d from the centroidal axis. Okay, so the theorem is saying that basically Ixc prime means like this axis is basically Ixc plus a d square. Okay, a is the area of that rectangle, which is actually ph. Okay, similarly, if I know the moment of inertia here, I can just go any like parallel axis of that one. Okay, it must have to be parallel though. Okay, you have to remember that one. So if you know the moment of inertia at the centroidal axis, basically you can change that one to any other parallel axis by adding AD square, where A is the area of that component and D is the distance from the centroidal axis of that component to the axis at which you are trying to find out your moment of inertia. Okay, so all the values given in your book is actually the moment of inertia at the centroidal axis, and you can just change that one to any parallel axis by adding this term here. Okay, now I'm going to show you some example. Okay, then you will see that how we are going to use this theory to find out the moment of inertia for different shape. Problem number 10-25. Okay, here is the figure. You can see they are just asking to find out the moment of inertia along the x-axis here. Okay, moment of inertia of this composite area. Now, first of all, we have to see that how many segments or how many components we can find out here, like how many regular shape we can find out here for the whole composite. Okay, you can do it like different ways, but just for this simplification, let's say I'm getting like this way. So this is my component A or component 1. This is 2 and this is 3. So if you add 1 plus 2 plus 3, then basically you will get the composite, right? So what we have to do, we have to find out, let's say we know the centroidal axis is at the middle here, and at that particular axis the moment of inertia of this square would be b into h cubed by 12. But they are asking not to find out the moment of inertia at the centroidal axis of component A. They are asking you to find out the moment of inertia at x-axis. So what we have to do here, basically we have to get the moment of inertia at the centroidal axis and then transfer that one from the centroidal axis to x-axis. Okay, so let's say for the first segment here, Ix is equal to Ixc plus AD square. Okay, that's for component 1. Similarly, I'll just write the whole thing here. Let's say for component 2, Ixc plus, let's say, A1 D1 square. Okay, so A2 D2 square plus Ixc, actually I'll just put like 1 here, 2 here, and 3 here, and then A3 D3 square. Okay, that's my total moment of inertia along the x-axis. Now this one is important, like where is the centroid of that thing here? Let's say for this one, the centroid is here, right? It's 2/3 from the apex and 1/3 from the base. So 1/3 from here to here is actually 1 inch, and from x-axis, so total D1 is basically 4 inch. Okay. Similarly, if you see for component 2, then basically here is your centroidal axis. The distance from here to here, that's actually your D2, that's actually 2 inch, right? Similarly, you can see for this one, the centroid is here. So 2/3 from the apex, 1/3 from the base. The total height is 6. So you can see the distance from here to here, that's actually your D3, which is also 2 inch. Okay, now I can just try to put all those values here and see what would be the moment of inertia for this composite body along x-axis. So you can see for one, this one is a triangle, so this one has to be BH cube, so 3 into 3 cube divided by 36, okay, plus AD square. What is A? It's half into 3 into 3. And your D1 is 4. So that's the contribution of component 1 for this moment of inertia along x-axis. Okay, so plus for component 2, you can see this is a rectangle, and IXC for a rectangle would be BH cubed by 12. So B is basically 3 into 3 cube divided by 12 plus A2. A2 is 3 into 3 and D2 is square. So D2 is 2 square. Okay. Plus, again, this is a triangle, so the moment of inertia at the centroidal axis here, that would be BH cubed by 36 plus AD square, which is half into 6 into 6, and D3 is 2, so 2 is square. So if you solve that one, then basically you will get 209 inch to the power 4. Okay, that's the unit, because you can see this is actually BH cube. So that's length into length cube, that's length to the power 4. Okay, so the unit for moment of inertia is either inch to the power 4 or centimeter to the power 4, meter to the power 4, feet to the power 4, something like that. Okay, now let's move forward. Problem number 10-47. Okay, here is the figure. This is my x-axis, this is my y-axis, and this is the composite area, and I have to find out the moment of inertia along the y-axis. So I have to find out IY. Okay, first of all, we have to just see that how many segment we can divide this total area. Okay, now you can see here actually there is a circle here which has a radius of actually 2 inch. So first of all, I have to find out that how many segment I can get from here, right? So once again, you can choose like different segment, that's up to you, but I'm just trying to show one of them that which would be the number of segment would be minimum. Okay, you can find out the other ways too. Okay, so here let's say I'm assuming that this is a solid, actually square, 6 square, plus this is 2, this is 3, and minus 4 here. Okay, so A1 plus A2 plus A3 minus A4, that's actually the area of the composite. Okay, so you can make it's not necessary, but if you want, you can make a table. That would be easier to do at the beginning. Okay, once you are more familiar with that system, then basically you can do it like just using the formula here. Okay, so I'm just showing that one in the table here. You can see in the table there is a segment. I have 1, 2, 3, 4 segments. Then this is the centroidal IY, and then this is A, this is D square, so this is AD square, so IY would be IYC plus AD square. Okay, now what would be, you can see this is my first segment. So let's say this is segment number 1. So IY should be BH cubed by 12, which is actually 6 into 6 cubed by 12. Okay, so I'm just, segment A is the solid. Okay, then I'll just subtract that one later on. So for y-axis, it's HB cubed by 12. Here is 6I, so this is 6 cubed divided by 12. The area of this one is basically 36, right? 6 into 6 is 36. What is my D? Okay, so here is my Y, and the centroidal axis at 3 here. For that one, the centroidal axis is also the center of this circle here. So this is the D1. Okay, so you can see that's actually 3, so that's 9. So AD squared is 36 into 9. So this one is basically, is this one, okay. Now let's say segment 2. This is my segment 2. Where is the centroidal y-axis here? That must have to somewhere here. If the total is 6, then from here to here that has to be 2, right? 1/3 from the base, 2/3 from the apex. Total is 6. So the centroidal axis of this one from the y-axis is actually 2 inch. And what's the moment of inertia? That would be these 3 into 6 cube divided by 36, because this is a triangle. Okay, the area would be half into 3 into 6. That's actually 9. D square is 2 square. That's actually 4. That's it. So AD square is 9 into 4. So the moment of inertia would be 3 into 6 cubed by 36 plus 9 into 4. Okay. Similarly, 3, segment 3, which is also a triangle, and you can see here that HB cubed by 36, H is 6, no actually 9, 6 plus 3, so 9 into 6 cubed divided by 36. Okay, now I need to know the area, which is actually half into 6 into 9. That's basically 27. The centroidal distance, that's I, Y, actually YC, sorry. So the distance from here to here would be total 6, 2/3 from the base, so that's actually 2 inch here. So that's 2 square, that's actually 4. So AD square is 27 into 4, and this one would be 9 into 6 cube divided by 36 plus 27 multiplied by 4. Okay, now I have to subtract the moment of inertia for segment 4. So that's my 4 here, and the I, Y, and Ix is same. That's pi r to the power 4 by 4. So 2 to the power 4 divided by 4. The area is pi r square. Then the d from y-axis to the parallel axis here, so that's actually 3, right? From here to here is 3. So 3 squared, that's 9. So AD squared would be pi into 4 into 9, okay? And if you subtract that one from here, I'll just put a negative sign here, and that would be pi 2 to the power 4 by 4 plus pi into 4 into 9. So if you get the total IY, so you have to add these 3 and subtract that one, and your answer will be 522 inch to the power 4. Okay. Now one of the most difficult thing here, what I see from my experience, is finding out the distance from the centroidal axis of a component to your actual y-axis. Okay, so you have to always remember that one, that actually the centroid of any rectangle is at the middle, okay, at the center of the rectangle, and for triangle that's actually 2/3 from the apex and 1/3 from the base, okay, of the height. And you already know that the center of circle is just the center, okay? So you have to be very careful with that. Now let's move forward. Problem number 10-35, okay? This one is asking that determine y prime, which locates the centroidal axis x prime for the cross-sectional area of the T-beam, and then find the moment of inertia about the x prime axis, okay? So basically, this is your x prime axis, which is the centroidal axis of the composite, okay? So first of all, we have to find out the y bar first, that y is my y bar. Then actually I have to find out my moment of inertia Ix prime for this T-beam here, okay? So first of all, we'll just try to divide that one, you know, some regular shape. So you can see that I can just do that one here using this one. Let's say this is 1 and this is 2. The first thing I have to know actually the centroid of this component 1. Let's say this one is here, which is, so this one we call that one y quick-lever 1, and that's actually, you can see from here to here is 250 millimeters, so this one has to be 125 millimeter, right? Similarly, we can find out the centroidal distance from the x-axis for component 2. So this is component 2 here, which is 50 millimeters. So the centroidal axis would be somewhere here, and the distance from here to here, that's basically, you can see from here to here is 250 plus 25. So 275 millimeter. Okay, so if I want to find out my y bar here, then by y bar would be y1 a1 plus y quick-lever 2a2 divided by a1 plus a2, right? So if I plug those values here, so 125 into area 1, which is 50 into 250, plus 275 into A2. A2 is also 300 into 50. Divided by 50 into 250, that's A1, and A2, which is 300 into 50. So this one is basically 206.82 millimeter. Okay, so the distance of this axis is from here to here is actually 206.82. Once I know that one, then I have to find out the moment of inertia along this x prime axis. Okay, so my I x prime, that has to be for the segment 1 is bh cubed by 12, so 50 into 250 cube divided by 12 plus AD square, right? So A is 50 multiplied by 250. And what is your D? You can see the D is the distance from centroidal axis of that component to this axis at which I'm trying to find out my moment of inertia. Okay, so that's actually basically this distance is y bar minus y1 quick-lever, right? You can see this minus, this is your y bar minus this one. That's actually the distance here, which is you are transferring your moment of inertia from the centroidal axis of this component to the centroidal axis of the composite. Okay, So this one is d1. So d1 we can just write that one, a formula like y bar minus y quiggly 1, okay, square. That's for your part 1. And then this one plus for the second component, which is 300 b into h cube, that's 50 cube divided by 12, plus ad square, which is 300 into 50, and d square means like the distance from here to here. That's actually your d2, which is basically, you can see that's actually y2 quiggly bar, okay, minus y bar, okay. So most of the time we usually follow the same formula, like y bar minus y2 quiggly bar. This one will come in negative number, but since that d is always square, so it doesn't matter, okay? So I'll just put that one here. Now if I change that one here, then let me write it here. That this one is (50) into 250 cubed by 12 plus 50 into 250. This one is basically 206.82 minus 125 square. That's for the component 1, and for component 2 is 300 into 50 cubed divided by 12 plus 300 into 50, that's your A, and your D is y bar minus y, actually quiggly 2 bar, so actually 275, or you can just say 206.82 minus 275 squared, and that's basically 222 into 10 to the power 6 millimeter to the power 4. So that's your answer, okay? This one is a little bit different than other one, because here you have to find out the centroidal axis of the composite first, and then you have to find out your moment of inertia at the centroidal axis of the composite, okay? Now let's move forward. Problem number 10-40. Okay, this one is also asking very similar thing, that find out the centroidal axis of this composite area, and then find out your moment of inertia along this x prime axis. Okay, so first of all I have to find out the y bar here, and once I get that one, then basically we'll try to find out the moment of inertia on that axis, right? So first of all, what we have to do, we have to just divide this area into 3 or 2, or like regular shape, right? So you can do that one different way. You can just do like 1, 2, and 3. You can also do 1, 2, and 3. But the most easiest one would be if I take the rectangle here, that's actually the big rectangle, this one, minus this rectangle here. Okay, so I have only two like regular shape. That would be much easier to handle. Okay, so let's say this is the bigger rectangle minus this smaller rectangle. Okay, so first of all, where is the centroidal axis of these big rectangles? Okay, so you can see the total from here to here is 4, so that must be somewhere here, right? So the distance here is total 4, so y quiggly 1, that has to be 2 inch, right? Now let's try to find out the y quiggly bar 2. So that's my second area, right? So this one is 3 inch. So my centroid would be somewhere here, which is 1.5 feet here. And if I measure that one from here, so that would be actually 2.5 feet. So y2 quiggly bar, that's actually 2.5 inch, inch. Let me say that repeat that one more time. You can see this is my area 2. So this one is 3 inch here. So the centroid of that one would be half, means like 1.5 inch from here to here. And if you measure that one from here, we know already that from here to here is 1 plus 1.5, that's 2.5. Okay, now let's try to find out my y bar first. So my y bar would be y1 quiggly 1 a1 minus y quiggly bar 2 a2 a1 minus a2. Okay, so if I plug that one here, then you can see 2 into a1, which is 4 into 8, minus 2.5, area of that smaller one is 6 into 3. Minus a1, which is 4 into 8, minus 6 into 3. So that's basically 1.36 inch. Okay, so the centroidal axis, x-axis, for this composite is at a distance 1.36 inch, right? Now let's try to find out the moment of inertia along this axis. Okay, so what we have to do, so let's say I x prime, that's actually I x c for 1 plus a1 d1 square plus, actually minus here, I x c for 2 plus a2 d2 square. Now what is d1 and d2? You can see d1, we know like d1 is actually y bar minus 1 quickly 1. So that's basically 1.36 minus 2. Okay, similarly here d2, actually I'll just put that one like this, that distance is always positive. Okay, whatever you get, you just make that one positive, and then you have to square that one, so it doesn't matter. Okay, so d2, that would be y bar minus y quickly 2, which is 1.36 minus 2.5. The absolute value. Okay. Now we can just plug that value here. So for this big rectangle, that would be ph cubed by 12. So 8 into 4 cube divided by 12 plus a square. A is 4 into 8. And d1 square is 1.36 minus 2 square. Okay, minus the moment of inertia at the centroidal axis for 2. This is my 2. You can see this is 6 into 3 cube divided by 12 plus a square. A is 6 into 3 and d2 is 1.36 minus 2.5 square. Okay, so if you do that one, then basically you will get that one 18.9. h to the power 4. Okay. Thank you for watching.